Hi guys, today I'll be doing on amplitude modulation and I'll be covering on AM concepts. So basically what you're supposed to know about amplitude modulation. Okay, if you take a look at this, this is your modulator and this is your modulating signal, or you call it intelligent signal. Is fed into the modulator with the addition of a carrier signal. It is usually of high amplitude and frequency. And the output that you're getting out of this modulator, it is called the modulated signal. Signal that has been or you can say signal that been modulated by or with the help of a carrier signal. With the help of this carrier signal, modulating the intelligent signal is fed inside the modulator and is being modulated as the output. Okay, now we'll look at closer on what is going to happen at the modulated signal and what is the look of the modulated signal. So if you take a look here, sorry for the drawing. So this part here, okay, goes something like that. This is your VC, or in other words, you can see it as the carrier voltage or signal voltage. When it goes here, this is the part where it is undergoing the modulation process. Where this particular part, to be precise, is your VM, modulated or modulating voltage. It's your modulating voltage. If you take a look at this part which is being compressed, is actually your envelope. So what does this do? Actually, envelope it connects positive and as well as your negative peaks of the carrier waveform. Okay, without further ado, let's move to the main part where you're comparing your Vm and versus your Vc. Therefore, you come up with your first formula. Vm over Vc is equivalent to your modulation index. This is your modulation index. Alright, when you get to know your Vm is more than your Vc, and therefore you're going to get a modulation that is larger than 1. This indicates distortion has occurred. Therefore, it is always, you need to make sure that your Vm, it is always less than your Vc. This is the first condition to obey in order to make sure that our modulating signal does not have any distortion or clipping effect as the output. So if you see your modulation, if your M or the modulation index is larger than 1, it causes clipping in the output signal. Alright, now let's look at the next part where we'll have to see the mathematical representation of AM. So I'm going to represent all of them in a mathematical form. So at first you were looking at your modulating signal, which is coming in this form. Vmt is equivalent to your Vm sine omega mt. Okay, and this is going in to your modulator, and here is your carrier with Vct is equivalent to Vc sine omega ct. Alright, and the output here you're gonna get Vam of combination of both. You're supposed to get in this form Vc plus your Vm sine omega mt, this whole thing into a sinusoidal form omega ct. So now I would explain how to get this expression. So that now I'll further explain about this expression so that you know how in detail how do we get the expression and what are the meanings of it. So from here Vmat is equivalent to Vc plus Vm sine omega mt sine omega ct. So if you take a look at this, I'm going to expand this formula so that we could further reduce it. So VC sine omega CT plus Vm sine omega CT sine omega MT. This expression, it is showing us that we are supposed to involve trigonometric function. So what are the trigonometric that we are supposed to enter? We have sine, so we take sine A, sine B equivalent to half cos A minus B and plus with cos A plus B. This is the trigonometric function, and if you substitute inside this, then you're gonna get VC sine omega CT plus Vm over 2 cos omega C minus omega M T plus cos omega C plus omega M T. So this is what expanded from the trigonometric explanation. So here from here I would like to apply the formula that we learned first, which is Vm over Vc is equivalent to your modulation index. So therefore my Vm is equivalent to MVc. Applying this into our formula, and therefore I'm going to get Vc sine omega CT plus MVc over 2 cos omega C minus omega M T. Okay, sorry guys, there's a mistake. This is supposed to be a minus, so I beg. So therefore minus MVc over 2 cos omega C plus omega M T. So this is our final equation. So if you take closer look at it, I could actually tell you that this is my voltage of my carrier. Voltage of carrier signal, and this here I could actually bring it down and express it in this way: omega CT, which is actually equivalent to 2 pi FCT. So therefore I would be knowing my frequency of my carrier from here. Alright, and here I have my Vm over 2. Why do I divide it by 2? It's because your sidebands, your output of the signal contains in the spectrum. If you take a look at the spectrum, this is VC and you'll have 2 sidebands. So therefore that's the reason why you take your Vm and divide by 2. It's because you need to know the voltage of each of these separately. That is what being done here. So you have to division of 2 in your formula. Okay, so from this I would be knowing my Vm, or in other words it's my voltage of modulating signal. And here this is omega c minus m, and if you take a look at this, is plus. So actually your lower side band is here and your upper side band is here. Okay, so how do I know which one is lower side band and upper side band? Okay, let's just expand this and see. Omega c minus omega m, which is actually 2 pi fct minus 2 pi fmt, directly meaning fc minus fm, it is actually my lower side band, equivalent to my FLSB, lower side band. So if you take a look at this spectrum, FLSB is located here and your FUSB is located here and your FC is here. So if I take my FC and minus away my FM, this is my FM. If I take my FC minus my FM, I'm going to get my FLSB. That's proven here. So this is one equation. And if you take this one here, omega c plus omega mt, which is 2 pi fct plus 2 pi fmt, indirectly means fc plus fm, which is equivalent to your FUSB. So if you take a look at here, FC, if I take FC and plus my FM here, I'm going to get the frequency of my upper side band, which is this formula. Okay. And another way to indicate your lower side band and upper side band is simply by looking at the symbol that is in this equation. If you look here, this is a negative symbol showing you that it is upper side band, and a positive symbol here showing you this is lower side band. Okay, so done with expression of modulated signal, modulated wave. Now I'm going to explain the sub formulas that is coming up from here. Okay, so now how do we find our maximum voltage? Okay, if I draw a signal now, if I draw the signal, okay, sorry for the ugly drawings. Alright, if you take a look here, always make sure that the frequency is remains same. Okay, forget about this part here. If you see, take a close look here, this is your VC. As I mentioned earlier, this is your VC, and this part here would be your VM, and how do I know what is my maximum value? A maximum value which is from the zero reference, which is here, up till your maximum, it is always my Vmax. And what about my Vmin? It is at your envelope, this peak lower point here, that is coming down to the crest or the zero reference is called your V min. That will be definitely your V min. Okay, so this is how you determine your V max and your V min. So from here itself you could now know what is the formula to gain V max. So V max now, V max is equivalent, if you take close look, it is actually from a zero reference up till your peak point, which is actually a combination of Vc and Vm. So therefore Vc plus Vm is going to get your V max. And the same goes to V min. V min would be equivalent to your Vc minus Vm. And there you would get these two formulas out. Oh, there's another way to prove my V min and V max in a better way, which is by using this formula. My Vm is equivalent to V max minus my V min over 2. Let's keep this as the first equation. And my Vc is equivalent to V max plus my V min over 2. Let's keep this as the second equation. So if I use these two equations, and there I would get my V min and also my V max. Okay, let's see how we do it. V max minus V min over 2. And therefore my V max would be equivalent to 2Vm plus V min. On the other side, Vc is equals to V max plus V min over 2. So my V max is equivalent to 2Vc minus V min. So if I equate these two equations, 1 is equivalent to 2, therefore I'm going to get 2Vm plus V min equivalent to 2Vc minus V min, and there you can see V min is equivalent to 2Vc minus 2Vm, and therefore you get your V min equivalent to Vc minus Vm. And the same goes if to go with the other one. And there you would get V max equals to Vc plus Vm. Okay. Now if you know how to play with these equations, V min, V max, Vm and also Vc, so therefore now you could also play with your Vm, which is equivalent to your V USF plus VLSF. What is this? Is upper side frequency and lower side frequency. If you plus them together, you're going to get your Vm. Or in other words, you can use it as this. As you know, your Vm is always Vm over 2, which means it is always the division, or where you have your sideband frequencies here, it it is always Vm over 2. Vm over 2. So therefore, passing them together, frequency of lower side and upper side frequency, and you're going to get your Vm. V of lower side frequency and V of your upper side frequency, and you'll be getting your Vm. And how if it's your Vm over 2, it's also equivalent to 1/4 of your V max minus your V min. Well, you know this is V max minus V min. It is actually equivalent to your Vm. So Vx minus V min and divided by a quarter times with a quarter, you're going to get your frequency, or sorry, voltage of your upper side band, upper side frequency, or either you get it as a lower side frequency. Okay, and as we all know, according to the spectrum, we are also able to find the bandwidth. So now you have FLSB and FUSB, and this is your carrier frequency. So from here, this area here is actually your FM, and this whole thing is now your bandwidth. So indirectly or directly means bandwidth is equals to 2 of your FM. Or in other words, you can take FUSB minus FLSB, and when you get, and you will still get your bandwidth. Okay, and I would like to emphasize one more thing here, is that about the modulation index. Modulation index. Okay. Modulation index. When your M is equals to 0, which means your Vm over Vc is equivalent to 0, there is no carrier signal input. Note that there is no carrier that is going inside your modulator. So there is no carrier that is going inside, therefore there is no modulation occurring there. That's why your modulation index is 0. if your m is equals to 0.5 or a value that is less than 1, it means that modulation occurred. Modulation occurred. And if you see your m is equals to 1, or in other words, distortion could have happened. And if your m is more than 1, then the distortion of overlapping occur. So in conclusion, saying that your modulation should always be less than 1 in order to have a modulation signal that is not distorted.